Okay, so a bit of good news, or at least the morning section thought this was good news. I don't know if you checked the Canvas announcements recently, but I decided to postpone the first exam by a week. Originally, it was supposed to be scheduled on the 24th, which would be next Thursday, the Thursday after this one that is going to happen next. And now instead it'll be on March 3rd. I just think that will make us all have a better time. Yes. Sure, in time that will come out. Yeah, yeah. I'll probably post that sometime early next week, something like that. Mm-hmm. So term one postponed. Now Thursday, March 3rd. Right? Is that the right date? I think so. In class. And if you've been attending remotely and or it happens that you test positive before then I would ask that you just take the midterm during the normal time that it would be offered during class and submit your answers on Canvas. But if that still is not, if you're too sick to do that, we can arrange some other alternative. Just let me know. Okay. And then a second announcement, don't forget that quiz 2 is this Thursday. Same story as last time. It will come out at 3 p.m. and you'll have 24 hours to do it. So 2 this Thursday. 3 p.m. 24-hour window. Again, I don't care how you turn it in person, in the envelope in my door or over Canvas, whatever. Okay, so as I recall, we were last discussing directional derivatives, right? Which we gave a definition for, and then I don't think we actually characterized what we can tell just by the sign of that definition. Or rather, this is actually what we said, right? So if we have some differentiable function of n variables at a point p hat, then we define the directional derivative of f in the direction u. Remember, u is a unit vector at the point p hat. To be the rate of change with respect to distance of the function at speed 1. Speed 1 indicating that this is a unit vector. And we had a theorem that said we can actually compute this as the gradient of the function f evaluated at p dotted with the unit vector u. Right? So you can think of this, before we go any further, we should talk about how to conceptualize this. Remember, we said the gradient of f somehow contains all the differential information that we care about the function f, right? So really, we're just looking for the components of the gradient of f that go along the direction of u, which is consistent with what we think about projection, right? We take a vector, in this case, the gradient, and see what part of it is parallel with the direction u. And that tells us the rate of change of the function in that direction. Now, I think this is actually where we left off. There's a formula for the dot product that uses the angle between the two vectors that you're dotting, right? Which is the magnitude of the first one, the gradient of f evaluated at p, times the magnitude of the second one, which, since we insisted this is a unit vector, just disappears since it's being multiplied in, and a unit vector has magnitude 1, right? Times cosine of theta, where theta is the angle between them. Now, suppose we were to ask What, given a function and a point, you have f and p hat, what direction will maximize this scalar quantity, the directional derivative? Yeah. Yeah, exactly. That is to say, we want to choose the unit vector that's parallel with the gradient. So again, going back to our interpretation, this means that, oh, what component of the gradient of f at p is parallel to our direction? Well, if we choose a parallel direction, then the entire magnitude of the gradient points in that direction. Okay. Okay. So the directional derivative in direction u of f at p is maximized in direction u equal to the gradient of f evaluated at p divided by the magnitude of the gradient of f evaluated at p, right? This is how we produce a unit vector, just to divide by its magnitude, right? It gives us a vector which has unit length pointing in the same direction. And in this case, what is the value of the directional derivative in direction u of f at point p? Well, that was a great explanation you gave. If the angle between them is 0, we plug that in to this formula. What's cosine of 0? Just 1, yeah. So we get the entire magnitude of the gradient of f at p. Okay. Opposite question. What if we are to minimize? What direction? Well, we consider the directional derivative. Yeah. So what would that make this value? Right, which makes this entire value, the directional derivative, 0. Can we have a directional derivative that's less than 0? Seeing some nods of yes. Yeah, if we look at an angle of negative pi radians, right? That is to say, if the gradient and the unit vector are anti-parallel, pointing in exactly opposite directions, then we'll have the value of the directional derivative be negative of the magnitude of the gradient, the least value, right? Another way to think of this is just, what is the max value of cosine and the min value of cosine? 1 and negative 1, right? So since this is just a fixed scalar at the point p, right, the magnitude of the gradient of f at p, it really just depends on cosine, right? Like here's the gradient, here's u, right? This is how the directional derivative changes as we change u. This maximizes cosine, this minimizes cosine. Okay, so we'll take this as the negative of the gradient of f at p by the magnitude of the gradient of f at p. And this, of course, gives us a value of the directional derivative in the direction u of f at p as the negative magnitude of f evaluated at p, the gradient of f evaluated. Okay, now here's the key fact that you said, right? We know that the directional derivative in direction u of f evaluated at p is equal to 0 if and only if u hat is perpendicular. to the gradient of f evaluated at p. So the first two of these facts, or you could say consequences of this formula, will be useful to us in analyzing how directional derivatives behave. The third of these is actually going to be essential to coming up with an alternative definition of what a tangent set is in the right setting, which we'll discuss shortly. First, I just want to go through a couple examples of how we use these first two types of information in regard to problems involving just directional derivatives. Okay. So let's let f of xy be equal to x times e to the y plus x cubed plus sine of y. And let's suppose at point 1 comma 0. 1 comma 0. Part A. We move toward the point 2 comma 3. What is the rate of change f with respect to distance and then secondly I would like us to answer part B, what direction you had. Should we move to maximize the directional derivative? And what is that rate of change? So why don't we take a couple of minutes and I'd like you to really try to talk to your neighbors here. You know, mathematics is social. You'll get a lot more out of your mathematics careers if you talk to your peers. Okay, maybe let's talk about it together. Let me hear your best ideas. What should we do first to address part A of the question? Yeah, go ahead. Yeah. So we definitely want to calculate the gradient of f. That's something that we'll need. Yes. Yeah, right. We'll look at the displacement vector from where we start and where we are headed toward, and make that a unit vector. Good. Then those are all the ingredients that we need to calculate um, what the directional derivative is. Right. So let's proceed. Of course, we did in words skip over the part where we'll evaluate the gradient at our starting point, but so we'll calculate the gradient, we'll evaluate it at this point, and then we'll calculate the displacement vector from our starting point to where we're headed, make it a unit vector, or come up with a unit vector that points in the same direction, and take the dot product of those two things, and that will give us the answer to part A. Okay, so what is the gradient of f evaluated at the point 1, 0? Well, let's use our notation here. We'll just calculate the gradient symbolically and then say evaluated at the point 1, 0. So just tell me the gradient first. What's the partial derivative with respect to x of f? Y plus 3x squared. Good. And the partial derivative with respect to y? Yeah, good. Extend to y plus cosine of y evaluated at the point 1, 0. Okay, and when we actually evaluate this, what do we get? We get e to the 0 plus 3 times 1 squared, comma 1 e to the 0 plus cosine of 0. Okay, I'm sorry, e to the 0 is 1 plus 3, we get 4. 1 times 1 is 1 plus what's cosine of 0? It's just 1, so we get 2 here. Okay, now as for u, we're going to look at the displacement vector with initial point 0, 1 and final point 2, 3, right? So 2, 3 minus 0. I'll employ this vector notation to emphasize that we're subtracting points to get a displacement vector. And then we'll divide by the magnitude of this displacement vector. Okay. Now, what do I get here? I get 1, 3 divided by the magnitude of 1, 3. What's the magnitude of 1, 3? Root of 10. Yes, good. Okay. Now all we have to do is take a dot product. Okay. Okay. So find that directional derivative in direction u evaluated at the point p to gradient 2 dot 1 over root 10 times 1, 3 together gives us what? I think this gives us 10 over root 10, or as more commonly denoted, call this root 10. Right? Okay. Good. How about B? Let's say here. Right, so we've already done half the calculation for part B, right? We already calculated what the gradient of f at p is. Now we just need a unit vector that points in that same direction, right? So say we want u to point in the same direction as the vector 4, 2, have magnitude 1. So take the vector 4, 2, divide by the magnitude 4, 2. Right? Okay, what's the magnitude of 4, 2? Sure. We'll just leave it as root 20. You can simplify it. Not necessary. Okay. So, and what's the max value? Value of the directional derivative in this direction? Well, actually, we've already calculated it, right? Yep. Yeah, it's just root 20. So fairly straightforward, right? Again, the only nuance of the directional derivative is remembering that it's just taking the part of the gradient that points in an arbitrary direction, right? The gradient contains all the information of where all the partial derivatives point, right? Which are the directional derivatives in terms of each of the coordinates of your space, x, y, z, or x1, x2, x3, up through xn. And dotting with an arbitrary vector u, in a unit vector, tells you how much of all those changes in your axes point in the direction u. Okay. So one more example, just to solidify this analogy that this somehow tells you about like what it would be like if you were walking around a mountain range. So analogy. This is really the question you asked me at the end of last class, but you would say steepest descent. Well, really that is only true in talking about space. Or talking about steepness in arbitrary dimensions, but it's a good thing to do. Okay. So here's another example. Let's say the elevation of a hill called Z. Given in terms of coordinates. X and Y by the equation Z of xy is equal to 400 minus 5x squared minus 3y squared with x, y, and z in feet. And we'll also say that it satisfies the inequality 5x squared plus 3y squared is less than or equal to 400. So scenario here is that you're looking at like a topographical map, right? Flat thing you're looking down on from, say, you're at the top of the positive z-axis and you're looking down, right? So you have coordinates x and y, and this condition that 5x squared plus 3y squared is less than or equal to 400 is something that says, for example, that you never go below sea level, right? You never have a negative elevation, which is usually measured from sea level. Have in mind for this type of example. Okay, so let's also suppose we're standing at the coordinates 2, 10 on the surface of the hill. Let me ask you, what direction should we travel for fastest ascent? So we have no regard for energy or difficulty of climbing. We just want to know if we go in a straight line according to some direction, how do we get to the top of the hill fastest? We have the constant speed 1. Travel the same speed no matter how steep it is the assumption here. So how do we address this? But see, this is the thing. Even if you know where the top of the maximum, the peak is, that doesn't mean we're looking at a local condition. Where can we start traveling to ascend fastest? We might have to reevaluate that later. But going in a straight line from where we are to where we're going to go won't guarantee us the fastest start. Okay, so that's actually what we're looking for. We're trying to find the direction in which we can start out going the fastest. Okay, that's kind of a subtle point. Yeah, we're looking for the steepest way up, because the more X and Y we go, the closer we'll get to the thing. And then we have to successively reevaluate that if we actually want to get fastest to the peak. But just to start, what direction should we start out in if we want to ascend most fastest? Okay, that's a good line of thinking. Yeah, but it's hard to like put that into analytical terms, right? I.e. an equation that we can manipulate somehow. Yeah. Yeah, we should look for where the direction that maximizes the directional derivative, right? Because the directional derivative tells you the rate of change with respect to distance. That is to say, what the directional derivative is telling you is how the graph of the function changes, right? Or steepness in this analogy when you're on the hill. Okay, So those are a lot of good thoughts, I have to say, about like what's actually going on. But once we have this interpretation, we can just apply these formulae that we develop. So, okay. Let's record this. We want to find direction u hat that maximizes the directional derivative in the direction of u. Sorry, our function is named z now. From our starting point, the coordinates 2, 10. Well, we just have a formula for that, right? We just find the gradient of z evaluated at this point where we're starting and divide by the magnitude of that vector. And that's the direction that we should go. Okay. So what's the gradient of z? Don't worry about evaluating right now. Just tell me what the gradient is. What's the partial derivative of z with respect to x? Yeah, negative 10x. And with respect to y, what do we get? Yeah, negative 6y. Good. Evaluated at the point 2, 10. Divided by, I'll just leave this here for now until we actually compute what the vector is. Okay, so what do we get when we plug in 2 and 10 here? We get negative 20, negative 60 divided by the magnitude of negative 20, negative 60. Okay, so, well, here's some algebraic simplifications. You can just factor a negative 20 out of the vector in all cases here. Of course, if I plug these components into the magnitude formula, I get a factor of 400 under the radical. So I can pull out a 20. In fact, I don't need these absolute value signs anymore. Yeah. Okay. Factors of 20 cancel. I get 1 over root 10 again times the vector 3. So that's that. Again, not so hard. You just have to interpret the verbal description of what you're given so that you can use the formula that you know. Yeah. Yes. Yeah, so that is to say, remember, to compute a directional derivative, we have to assume that we're having a unit vector, u. So the maximum and minimum are given by, respectively, the unit vector that points in the direction of the gradient and the unit vector that points in the opposite direction of the gradient. I think that's what you were saying, right? Yeah. Good. So now I want to go back to a topic that we've discussed at some length already and relate it to some of the stuff that we've done since we talked about that. Namely, I want to talk about the relationship between level sets and gradient vectors. So we talked about how to define a tangent set to the graph of a function at a point on that graph, right? That was the definition of tangent set that we gave. Now what we want to do is when we get to the main applications of this course, the last third of the course, we will be primarily concerned with functions of 2 and 3 variables. Okay. And that's in part because when things are nice enough, the level sets of a function of 3 variables, for example, is a surface, right? A function of 3 variables has a graph that lives where? How many dimensions does it take to draw a graph that for a function that has 3 variables? I've seen a couple people show it with their hands. You want to say? Yeah, 4. You have to go up to R4 to graph something with 3 variables. Now, when we were talking about level sets, we kind of conceptualize them as cross sections, right? And when we take a cross section, we go down a dimension, right? So if the graph of a 3 variable function lives in 4 dimensions and is conceived of as a 3-dimensional object sitting in 4 dimensions, when we take a cross section, we get a 2-dimensional object sitting in 3 dimensions, i.e. a surface in R3. Okay, so our discussion here is guided by the motivation to come up with a good notion of what it means to describe a tangent set to a level set in a way that when we consider level sets of functions of 3 variables, it agrees with the definition of tangent set that we gave for the graph of a function of 2 variables. And that was a lot to take in, but that's just the overview of everything that we're going to say in this section. Okay. Also, I really want you to be comfortable thinking about the dimensionality of graphs of functions. I want you to be able to look at the definition of a function and know exactly, it's like, okay, it takes this many dimensions to graph it, and the actual graph looks like this dimensional thing in this dimensional space. And now we want to do the same thing for level sets and the tangent sets of level sets. Okay, so let's just remember the definition of level set. Recall a level set for a real value function of n variables f of x1, x2, xn, or as we sometimes write in shorthand, f of x hat is the set of points x hat in Rn satisfying the following. F of x hat is equal to c. C is a constant. Okay. This is just the basic definition of level set. And we also looked at a specific class of these. Since f is a real value function, we can use f to generate certain constants to form level sets, right? That is to say, if p hat in the domain of f, then the set of points in Rn satisfying f of x hat is equal to f of p hat is the level set containing p. This phrase is a little off, right? Because really, a level set is a subset of the graph of f, which it's weird to say it contains p. It contains the point p comma f of p, right? F of p being a constant, since f is a real value function. We can find the level set at the output of f when evaluated at p. So we just call this the level set that contains the point p. So it's best if we look at some examples here. And maybe you'll recognize this one. Let's take a function f of x comma y, x minus y squared. What does the graph of this function look like? Everybody look at that website that we had a glance at together. Study the quadratic surfaces. Anybody remember this one describes? That's okay if you don't, but this is something to practice. You know, again, you don't have to know right away. Most times you'll have a calculator on you. I will probably be able to tell you this, but to save yourself some time and headache if you remember some basic facts about what the graphs of these various quadratic surfaces. This is a static. Right? This is one of these. Coordinate axes here. Z x goes out this way. Y goes out this way. Okay. Geez. I really should slightly more accurate. Why don't we say 0 origin? Okay, that's slightly better. All right. So why don't we look at some of the level sets of this function f? First of all, what are the level sets of this function? Just give me the dimension. What dimension thing will we get when we take cross sections of this saddle? One. Yeah, I see. You're saying one. Good. Meaning there'll be curves, right? Okay, so curves we have to draw in R2, right? We need one more dimension than the dimension of the thing to draw it. Okay. So what happens when we look at the level set? Let's first look at the level set. F of x comma y equals x squared squared is equal to 1. What does the graph of this look in like in the xy plane? This looks like a hyperbola. How's it orient? Yeah, good. So, hyperbola. Maybe it would help if I drew the asymptotes first. So we approach the asymptotes. This is f equals 1 for sure. What happens if we go to f x y equals 2? What does that level set look like? They're a little further out, they're a little shallow. Yeah. Right, so something like this. It's 2. What if I go in the other direction, more negative from level set 1? What do I get? When x, y, 0. Yeah, let's actually do a little bit of algebra here. Right? This is equal to 0 is equal to x squared minus y squared. This implies that x squared is equal to y squared, right? Just adding y squared to both sides, which is the case when y equals x. Or perhaps one of them could be negative, since we took the square root. Or negative y. So our level set when our constant equals 0 is just our pair of asymptotes. It's markedly different than F1 or F2, right? Because we have two intersecting we have two intersecting lines, right? So remember our whole conversation about smoothness? This level set is not smooth because you can't define a tangent line right here. You come from different directions and the tangent line means different things. Okay. Just one more. What happens if I continue to go more negative? If I look at the level set where f of xy equals -1. Yeah. Yeah, like reoriented, right? That is to say, something like it's -1. So these are all in the family of level sets of this function. And you remember when we looked at that website together, this corresponds to us just taking a plane at a fixed z value and changing the value of z. Right? We're just sliding a plane up and down. And when we hit 0, that's when we just get a pair of intersecting lines, right? Remember, we kind of made a point of this when we were looking at those computer images. So keep this example in mind. We're going to come back to that in just a moment. And we're going to try to characterize when exactly our level sets are smooth and when they have singularities, points where they're not smooth. Okay? Because remember, our broad goal is to be able to define tangent sets. So we have to be able to define what tangency means at every point of the level set. We want to do that, which we can't do right here. We're going to look at why that happens, why that is. So let's look at a couple more examples before we do that. Let's consider the function of three variables, s of x, y, and z, by x squared plus y squared plus z squared. And consider x squared plus y squared plus z squared equals c. Just c an arbitrary constant. We want to see if we can broadly characterize the possible level sets of this function s. That is to say, as c varies, what are the level sets of s? Kind of like what we did here, right? We had three cases in this example. We had the case where our constant was positive, in which case we had a hyperbola that opened out this way. Our case where c was 0, in which case we had the singular level set that had a sharp intersection. And then for c negative, we had a hyperbola that opened this way. Right? So let's do a similar analysis here for this function s. Okay, so this time let's maybe do it in order, quote unquote. What happens if c is strictly negative? We would get as the level sets function s. Nothing. Why is that? Yeah, no matter what the values of x, y, and z are, we're squaring each of them and adding them up. So the minimum value we could get for this function is 0, no matter what x, y, and z are. So in this case, the level sets are all set with no elements. The empty. So we call that set with no elements. Sometimes you'll see this denoted as a circle with a slash through it. It's just notation for a set with no elements. Okay, so this contradicts what I said originally, right? Where if we want to find a level set, it's a slice of the graph minus one dimension. Right? Take a cross section and you go down a dimension. The empty set has no dimension, or according to some authors, dimension -1. The graph of this thing is a three-dimensional thing that sits in R4. So again, we're going to characterize what's going on, what's necessary. What are the necessary hypotheses to make my claim true? This is just an easy to describe case where things go wrong. Okay. All right. So what happens if c is equal to 0? The level set there, yeah, both. Sorry, all three x, y, and z have to all be 0. That is to say, the level set is just a single point. Okay. The level set is just point 0, 0, 0. And again, contradiction of what I said. A single point is 0 dimensional. Again, this is three-dimensional thing in R4. Okay. So what happens? C is strictly positive with the level sets. Anybody? Sure, just answered a lot of questions. Snap at this. Yeah. Okay, so how do we describe that as potentially, ideally, we would like to describe that as a two-dimensional thing in three-dimensional space. Do you want to just That's true. All the level sets will have infinitely many points when the constant is greater than 0 for this function. But how will they be arranged? Yeah. Not quite. Okay, so maybe this is a point of confusion, right? Here I say level sets. That is to say, there's a level set for each constant less than 0. Here I just say the level set because we're only considering a single point 0. We're actually looking at a family of level sets, just like in the first case, one for each positive constant. So that is to say, what I'm really looking for is a description. If I pick one particular positive C, what does that set that satisfies x squared plus y squared plus z squared equals c look like? Which we have some hope of actually saying, because it should be representable as a two-dimensional object in three-dimensional space. Well, yeah, so but we're allowed to choose anything for x, y, and z. Yeah.
Each x, y, and z.
Not quite, not quite. So let's do a for example. For example, if x squared plus y squared plus z squared is equal to 1, what does this describe in three-dimensional space? A sphere of radius 1, right? We get a sphere of radius 1. Good. So in general, for a positive c value, we have the equation x squared plus y squared plus z squared equals c. That gives us a sphere of radius root c. Should write that in symbols. Root c for the level set. Okay, so I'm trying to emphasize this a lot. There's no real hope of trying to graph S, but we do get some idea, some geometric intuition by examining its level sets that behave like I said, that behave that when I take a level set, I get something of one dimension lower than the graph. This function S describes a hypersphere or a four-dimensional sphere. That is, any way you take a cross section of it, you get some sphere. Okay, so this is kind of how we imagine these things that live in four-dimensional space. We look at their level sets. This is one way that we try to extend our geometric intuition beyond what we can visualize by examining these types of objects, level sets, which is why this is a good jumping off point for extending the notion of what tangency means, right? We want to reconcile our general definition of what a tangent set is to a function of arbitrarily many variables, to studying the tangent sets of their level sets, which reduce the dimension by one, which help us conceptualize things better. Okay. So in the last couple of minutes, let me just say some general remarks, and then we'll pick up trying to define what a tangent set is to a level set on Wednesday. Okay, so by our discussion of directional derivatives, here's what we know. We didn't really talk about this much when we talked about directional derivatives, but the directional derivative in direction u of some function f evaluated at p equals 0, if and only if u is normal to the gradient of f evaluated at p. Right? That was point number 3 that we talked about at the beginning of the day today. Yeah? Okay. So what this means, the rate of change at p in the direction u is 0. Right? Rate of change of f. Sorry, capital F we're using now. In direction u 0. What does it mean if a function has rate of change 0? Just in very broad terms. Think calculus 1. Yeah. It's a constant. Yeah, exactly. Right? So in direction u, f equals c, some constant. What does this look like? A level set. Yeah? Okay, so we're right there. We're right near where we can define what tangency of a level set means. We have some rate of change being 0, where f is a constant. We're going to use a dot product somehow. So we'll pick that up on Wednesday. Okay. Good. Don't forget the quiz is on Thursday. And oh yeah, I'll have the physical copies for those of you who turned in physical copies of your quiz 1 back on Wednesday. I just keep forgetting to bring them. They're graded. The grades are on Canvas, but I'll bring in your copies. Sorry.